the first column of our table look like for the equation y equals x plus 1? When x equals 0, what's y? 1. When x equals 1, what's y? 2. In other words, we're subbing the x value and adding 1 to it, aren't we? So it just keeps going up by 1. As long as the x's go up by 1, the y's end up going up by 1, don't they? So that should be, you should have seen a pattern developing there. As the x's were going up by 1, so were the y's. How about the next column? When we have the other equation, y equals 5 minus x. When x is equal to 0, what's y? 5. Next one? 4. Okay, in other words, it keeps going down by 1, right? As x goes up by 1 in this one, the y's are going down by 1. Okay, this is kind of like if you had made tables.
Candace, hire to the senior office, please. Candace.
If you had made tables to help you problem solve the bag problems that we did for today, this is kind of like that, where, you know what, one of the columns would be, well, here's all the ways I can get those tickets to add up to 22 tickets. Here are all the ways I can make the tickets add up to the dollar amounts of the tickets, add up to $74. And yet there was really only how many solutions? How many ways you could make both happen? There's only one, wasn't there? Same way with the coins. So one column would be what in our table? In the coins one. All the ways like Allie did to get $1.25. And the other column would be all the ways to get 19 coins. Yeah, because, you know, we could have 1 nickel and 18 dimes, right? 2 nickels and 17 dimes. And we could just go on. There's all kinds of ways to get 19 coins out of nickels and dimes. And there's all kinds of ways to get $1.25 with nickels and dimes. But there's only one way to get what? To get both. There's only one way to get both, to make both happen. Do you see that happening in this table? We don't know what these are about. We just know we have two different situations. I just kind of like helped refer it to, well, maybe one of them is the tickets adding up to 22. Maybe the other one is the value of them adding up to $74. We only got one way to get worked. How does that show up in this table that we have no idea what this table is about? Anybody see how it's showing up in the table? I think it's right here. When x equals 2, y equals 3 for both situations. It satisfies both of them. So it's, it's kind of like saying we can only have x equals 2 and y equals 3, and that's what's going to satisfy both of them. It's the only maybe ordered pair that satisfies them. But are we sure? So right now I'm predicting that how many ordered pairs do you think are solutions to both equations? I'm thinking there's just one. That's all we see in the table anyway. Let's go to our graphing calculators and put into y equals into y sub 1, so clear out what's in there. Does everybody have a calculator, by the way? Somebody probably got shortchanged here, right? Okay. In y sub 1, we're going to put the x plus 1. In y sub 2, we will put the 5 minus x. And then, after you have those in, where do we get the table? Second graph. And you should be able to find in the table, it should look a lot like this. You have a column that has x values. You have a y sub 1 column with some y values. You have a y sub 2 column with some y values in that one. If you go find this part of the table from x equals 0 through x equals 4, it should match ours, does it? Okay. Now, did we make all the possible ordered pairs that we possibly could? Did we make this table for as many things as really could be in it? No, we didn't even touch on the negative x values, did we? So I want you to scroll through that table, and I want you to see if you can ever find another x value that has, in the y columns, the y's match up. They have the same exact y value. Like x equals 2 has the same y values of 3. Is there anywhere else in that table? We'll search some in negative x values. We'll search beyond positive 4. And by watching what's happening in those y values, do you think you ever would? You probably would. Okay, now I want you to press zoom 6. I want you to graph this. Zoom 6 will give you a nice graph. What's the graph showing us? What's happening on the graph? They're both a linear equation, so wait. We have two lines and they're intersecting, you said once? Okay. So everybody see that on their graph? I wonder where they're intersecting at. 3, 3? It's got to be a point they have in common. In other words, they have to have the same x value and the same y value. So is it 3, 3? I think it's 2, 3, isn't it? So let's go back to our notes here. It says, let's verify with the graphing calculator. What does the table show? There is only one x value. With the same y value for both. There's only one x value in that whole table that has the same y value for both of these equations. It's the only one they have in common. And how does this show up on the graph? Well, the lines intersect at that point. Comma, what is the point? What did we say? 2, 3, ordered pair 2, 3. So I'm guessing, crazy guess of mine, that if we were to make equations for those two bag problems that we did, so if we made equations for those ticket problems, we could come up with two equations if we could find where the lines intersect. What do you suppose that point of intersection would be? 18, 4, or it could be 4, 18, depending on which one we assign the x value and which one we assign the y value, right? Because we're 4 of one and 18 of the other, and just depending on which one we call x and which one we call y. I bet those lines would intersect at that point. But we don't really know how to write the equations for them quite yet, but we're going to get there. What do you think would happen with the coins problem? Pardon? 13, I think it's 18. So there were 6 of the dimes and 13 of the nickels, so depending on which one you assigned which value, it would be 613 or 13.6. Those lines would probably intersect at that point. So when we have two unknowns, we should be able to use graphing. We should be able to use equations to help us solve them. So turn your calculators off for now. When two or more linear equations containing two or more variables work together, it is called a system. That dash doesn't need to be there. A system of linear equations. They are working together. It was kind of like the coins. The nickels had to work together with the dimes, and they had to form a total of 19 coins, and they had to value $1.25. They had to work together to help us get the answer. So we would be able to set up an equation for each of a couple of equations and call them a system of equations. The solution of a system of linear equations with two variables in it is an ordered pair. When you give the solution 6 dimes, 13 nickels, it should be written as an ordered pair. 18 child tickets, 4 adult tickets, it should be written as an ordered pair. because they are the x and y values that make both equations in the system true. So note up here, I said when there's two or more linear equations, typically we will just work with two. Sometimes there can be 3 or however many. And then 2 or more variables. Good news is this year in Algebra 1 we only have to work with 2 variables because we want to be able to do it on the coordinate plane, so we only work with 2. So on a graph, to find the solution of a system, you need a point they all have in common. Therefore, you're going to look for their point of intersection. When you are solving by graphing, you need to estimate where do you think those 2 lines are intersecting. And then we're going to check it out to make sure that it really does make the equations true. It has to make both of them true. Any clarification needed on this side? Okay, then let's go back and start. Solve by graphing. Putting this, what we call, remember, our set notation, but it's bigger, it's around both of the equations. That is our indication that these 2 equations are not separate of each other, they're working together. They're a system. So we have y equals 3x plus 1 and y equals negative x plus 5, that we have to find the solution that makes both of them true. Not just one of them, but both of them. Are they in graphing friendly form? Since we're going to solve by graphing. Okay, go ahead and identify the slope and y-intercept for both of them then. If you say they're ready, then let's do it. When we graph these, because again, this rule is not changing, a minimum of 3 points for each line, unless the graph doesn't support it, you like go off the graph and have to make your own grid lines. Graph them one at a time. Take the time to graph the 3 points for one of them, draw the line, and then graph the other so that you're going to be able to tell where these lines go. So go ahead and get the first one graphed. And of course, you should still keep asking yourself the same question that we've been asking all along. After you're done graphing it, does the behavior of the line match the slope? It has a positive slope, this first one, so it should be rising from left to right. So at this point, I'm feeling okay about mine. And then I'm going to go on to, after I have my line drawn for that one, I'm going to move on to be graphing the second one. Okay, I gotta find where I belong again now. Let's see. 5. I love when I do that. Green is supposed to be at 1. Wonderful. Oh, I don't know if I can get this back. Oh, right there. There. So much fun. Okay, let's draw the line instead of move the graph. Okay, there we go. Did I put it back right? I think so. Okay. Can we tell where they're intersecting at? What's their order pair? What's the order pair we estimate is the solution? In other words, right here, what's that one's name? 1, 4. Remember, the solution is written as an ordered pair. So we are saying that the solution, we believe, is ordered pair 1, 4. But we don't get to just assume that is correct. We have to do check problems today. That's why you only have 7 problems to do. Because not only will you graph them, but then you will check your solution to make sure it makes both of the equations true. So we have y equals 3x plus 1, and we have y equals negative x plus 5. Each of them have to have the x and the y value from that point subbed in. So 4 is going in for y, 1 is going in for x, and we just keep simplifying it down. We don't have any solving to do here. We just say, well, 4 is 4. 3 times 1 is? 3 times 1 is?
3.
3. And we're not quite done because we're going to say, well, this side is 4 and that side simplifies to 4. So we can say, oh, it made it true. It's a true statement. 4 does equal 4. Yes, that's how involved your check problem should look. Yes. Substitute in, start simplifying down, end up with a statement that we can clearly see 4 equals 4. There's no argument there. Nobody has to think. Okay, and then we do the same thing in the other equation. It has to make this one true also. It can't just make one true and you can say, oh, it made it true, good enough. It has to make both of them true. So 4 equals negative 1 plus 5, because that negative sign was not part of the x. What's negative 1 plus 5? Happens to be 4. Checks out. So we are going to be content to say this is the solution for that system. It's the 1 of something and the 4 of something else that makes both situations true. Any questions on that one? Okay, let's go to graphic calculator and check it out. See how we did. These are already in soldiers and forms. We can steal them as they are. So go to y equals, clean out the ones that you had in there. Type in the 3x plus 1, the negative x plus 5, negative sign, not subtraction sign. Press graph. Does it look like yours, mine, all of ours? Where can we check to see if we have the right order here? Second graph in the table. We're going to go in the table to where x is equal to what? In the table to where x is equal to what? 1. And what should be true? It should be 4 in both of the y's. Go check it out. Here we do it right. Okay. Graphic calculator is handy for this one because they were already in slope intercept form. That's the only way we can put them into the graphic calculator is in slope intercept form. But notice our problem number 2. Are they in graphic friendly form? No. And look at what I say. It will be best to put these in slope intercept form. Some of you would be like, well, wait a minute, I would rather make a table. I don't know why, but if you're crazy enough to want to make a table for each of them, pick x values and get y values to help you get the graph, you could do that. Or you could use the x and y intercepts, but that only works when x and y intercepts are nice integer values. Otherwise, if it comes out to 1 2/5 for the x-intercept, oh, I don't know if that will be so accurate. So I'm thinking that putting them in slope-intercept form should be the best choice there is, and we've been doing a lot of that. So let's do that. We have our first equation here, 3x plus y equals 4. What should we do to get y alone? Do what? Subtract 3x. And now we have y equals 4, subtract 3x. If we don't do this well, we're setting ourselves up for not being able to solve these by graphing. We have to be able to rename the equation properly so that we'll get the right line, so that we'll be able to get the right solution. So I am going to suggest to many people in here that they maybe should do this. Change that subtraction to add, and that 3x will become a negative 3x. Now it's y equals, well, b plus mx. What is our m value? Negative 3, not the 4, right? It's what x is being multiplied by. What's our b value? Positive 4, okay? We'll graph that one before we mess with the other one. Go ahead and get that one graphed. This one should do what? What should its behavior be? Fall from left to right, okay? According to our slope intercept form name anyway. Okay, Now we'll go over and we will get our other equation into slope-intercept form. Suggestions for that one? Subtract x, okay. What do we have after we subtract x? Negative 2y. So again, I'm going to highly suggest that when we see that subtraction, we change this to add the opposite. So we bring the correct thing down. It is negative 2y, and that's important. 6, subtract x. Oh, there's another subtraction again. What can we do with that subtraction? Change it to add, and this is going to become a negative x. And you know what? I think it would be even helpful to slip a 1 in there. Make it a negative 1x. That's what negative x means. Because what are we going to do next? Divided by what? Negative 2. So we're going to divide every piece by negative 2. Every piece, not just the ones that look friendly. Oopsie, that's not an equal sign there. That should be a plus sign. So our slope-intercept form name for our equation that started in standard form is a negative divided by a negative is a positive. You can't take a whole number of 2's out of 1, so you just leave it as a fraction and call it 1/2 x. Okay, the slope of this one is 1/2. The y-intercept is negative 3. Go get that one graphed. It's always fun to try and draw these lines. Okay, do you think you have the point of intersection? Do you think you got the slope? What is it, Macy? What do you have? 2, negative 2, okay? So below the graph, let's put that we think it's 2, negative 2, where it is intersecting. My lines are a little bit off, but it's because I have to deal with the smartboard. So now we're going to check it to make sure. Stop, because I already know what you're doing. You're putting it into the slope-intercept form name, aren't you? Huh. Well, it just might check out in there because that's what you use to help you graph it. But if we really truly want to make sure we did this whole problem correctly, where do you suppose we have to check our solutions at? In the original names, in those 3x, what was it again? I gotta see, go back again. It was 3x plus y equals 4. And the other one was, remember, x minus 2y equals 6. Thank you. That's what you got to check them out in. Don't check them out in your new names for the equations, because guess what? That's what you graphed from. Of course, those are going to check out. If we want to make sure we did the whole problem correctly, we need to check our ordered pair solution in the original names. So check them out in that one. So 2 is going in for x, negative 2 is going in for y. Going from that to 4 equals 4 would not be called a check problem. 3 times 2 is 6. We have 6 plus negative 2 now. We're still not done. 6 plus negative 2 is 4. Now we can say we're done with that one. It does check out in that one. And now we'll go over to our other one and substitute in 2 for x, negative 2 for y, and not just magically say that that is 6 equals 6. Because this is where lots of students would try to make themselves and me even try and think that they can make me believe that they know what they're doing here. I'm going to change this to add the opposite. That's going to be a negative 2 there. So I have 2 plus -2 times -2. +4. Still not done. Even though you're like, well, of course, 2 + 4 is. Let me write it. Checks out in that one also. Students, if you do not check them in the original name, you check them in the, after you've renamed them and you get to class and I show a different solution on the answer key and you say, but mine checked out. Why? And I'm going to look at your paper and I'm going to say, did you check them in the original name? And I'm going to see that you didn't. And I'm going to be like, well, because you're checking in the wrong equations. And of course it's going to check out in those. Okay, so you have to check back in the original. Questions at all? Okay, get on the sleeve.